Steel is an alloy of iron and other elements, primarily carbon, that is widely used in construction and other applications because of its high tensile strength and low cost. Steel's base metal is iron, which is able to take on two crystalline forms, body-centered cubic and face-centered cubic, depending on its temperature. It is the interaction of those allotropes with the alloying elements, primarily carbon, that gives steel and cast iron the range of unique properties. In the body-centered cubic arrangement, there is an iron atom in the center of each cube, and in the face-centered cubic, there is one at the center of each of the 6 faces of the cube. Carbon, other elements, and inclusions within iron act as hardening agents that prevent the movement of dislocations that otherwise occur in the crystal lattices of iron atoms. The carbon in typical steel alloys may contribute up to 2.1% of its weight, varying the amount of alloying elements. The presence in the steel, either as solid elements or as precipitated phases, retards the movement of those dislocations that make iron comparatively ductile and weak, and thus controls its qualities such as the hardness, ductility, and tensile strength of the resulting steel. Steel's strength compared to pure iron is only possible at the expense of iron's ductility, of which iron has an excess. Steel was produced in bloomery furnaces for thousands of years, but its extensive use began after more efficient production methods were devised in the 17th century, with the production of blister steel and then crucible steel. With the invention of the Bessemer process in the mid-19th century, a new era of mass-produced steel began. This was followed by Siemens Martin process and then Gilchrist-Thomas process that refined the quality of steel. With their introductions, mild steel replaced wrought iron. Further refinements in the process, such as basic oxygen steelmaking, largely replaced earlier methods by further lowering the cost of production and increasing the quality of the product. Today, steel is one of the most common materials in the world, with more than 1.3 billion tons produced annually. It is a major component in buildings, infrastructure, tools, ships, automobiles, machines, appliances, and weapons. Modern steel is generally identified by various grades defined by assorted standards, organizations, definitions and related materials. The noun steel originates from the Proto-Germanic adjective Stachlischen, which is related to Stackler. The carbon content of steel is between 0.002% and 2.1% by weight for plain iron carbon alloys. These values vary depending on alloying elements such as manganese, chromium, nickel, iron, tungsten, carbon, and so on. Basically, steel is an iron-carbon alloy that does not undergo eutectic reaction. In contrast, cast iron does undergo eutectic reaction. Too little carbon content leaves iron quite soft, ductile, and weak. Carbon contents higher than those of steelmaking alloy, commonly called pig iron, that is brittle, while iron alloyed with carbon is called carbon steel. Alloy steel is steel to which other alloying elements have been intentionally added to modify the characteristics of steel. Common alloying elements include manganese, nickel, chromium, molybdenum, boron, titanium, vanadium, tungsten, cobalt, and niobium. Additional elements are also important in steel: phosphorus, sulfur, silicon, and traces of oxygen, nitrogen, and copper that are most frequently considered undesirable. Alloys with a higher than 2.1% carbon content, depending on other element content and possibly on processing, are known as cast iron. Cast iron is not malleable even when hot, but it can be formed by casting as it has a lower melting point than steel and good castability properties. Certain compositions of cast iron, while retaining the economies of melting and casting, can be heat-treated after casting. rusting to make malleable iron or ductile iron objects. Steel is also distinguishable from wrought iron, which may contain a small amount of carbon but larger amounts of slag. Material properties. Iron is commonly found in the Earth's crust in the form of an ore, usually an iron oxide, such as magnetite, hematite, etc. Iron is extracted from an ore by removing the oxygen through combination with a preferred chemical partner such as carbon that is lost to the atmosphere as carbon dioxide. This process, known as smelting, was first applied to metals with lower melting points, such as tin, which melts at about 250 degrees Celsius, and copper, which melts at about 1100 degrees Celsius, and the combination, bronze, which is liquid at less than 1083 degrees Celsius. In comparison, cast iron melts at about 1375 degrees Celsius. Small quantities of iron were smelted in ancient times in the solid state, by heating the ore in a charcoal fire and welding the clumps together with a hammer, squeezing out the impurities. With care, the carbon content could be controlled by moving it around in the fire. All of these temperatures could be reached with ancient methods used since the Bronze Age. Since the oxidation rate of iron increases rapidly beyond 800 degrees Celsius, it is important that smelting take place in a low-oxygen environment. Unlike copper and tin, liquid or solid iron dissolves carbon quite readily. Smelting, using carbon to reduce iron oxides, results in an alloy that retains too much carbon to be called steel. The excess carbon and other impurities are removed in a subsequent step. Other materials are often added to the iron-carbon mixture to produce steel with desired properties. Nickel and manganese in steel add to its tensile strength and make the austenite form of the iron-carbon solution more stable. Chromium increases hardness and melting temperature, and vanadium also increases hardness while making it less prone to metal fatigue. To inhibit corrosion, at least 11% chromium is added to steel so that a hard oxide forms on the metal surface. This is known as stainless steel. Tungsten interferes with the formation of cementite, allowing martensite to preferentially form at slower quench rates, resulting in high-speed steel. On the other hand, sulfur, nitrogen, and phosphorus make steel more brittle, so these commonly found elements must be removed from the steel melt during processing. The density of steel varies based on the alloying constituents but usually ranges between 7,750 and 8,050 kilograms per cubic meter, or 7.75 and 8.05 grams per cc. Even in a narrow range of concentrations of mixtures of carbon and iron that make a steel, a number of different metallurgical structures, with very different properties can form. Understanding such properties is essential to making quality steel. At room temperature, the most stable form of pure iron is the body-centered cubic structure called alpha iron or alpha iron. It is a fairly soft metal that can dissolve only a small concentration of carbon, no more than 0.005% at 0 degrees Celsius and 0.021 Wt% at 723 degrees Celsius. The inclusion of carbon in alpha iron is called ferrite. At 910 degrees Celsius, pure iron transforms into a face-centered cubic structure called gamma iron or gamma iron. The inclusion of carbon in gamma iron is called austenite. The FCC structure of austenite can dissolve considerably more carbon, as much as 2.1% carbon at 1148 degrees Celsius, which reflects the upper carbon content of steel, beyond which is cast iron. When carbon moves out of solution with iron, it forms a very hard but brittle material called cementite. When steels with exactly 0.8% carbon are cooled. The austenitic phase of the mixture attempts to revert to the ferrite phase. The carbon no longer fits within the FCC austenite structure, resulting in an excess of carbon. One way for carbon to leave the austenite is for it to precipitate out of solution as cementite, leaving behind a surrounding phase of BCC ion called ferrite that is able to hold the carbon in solution. The two, ferrite and cementite, precipitate simultaneously, producing a layered structure called pearlite, named for its resemblance to mother of pearl. In a hypereutectoid composition, the carbon will first precipitate out as large inclusions of cementite at the austenite grain boundaries, and then, when the composition left behind is eutectoid, the pearlite structure forms. For steels that have less than 0.8% carbon, ferrite will first form until the remaining composition is 0.8%, at which point the pearlite structure will form. No large inclusions of cementite will form at the boundaries. The above assumes that the cooling process is very slow, allowing enough time for the carbon to migrate. As the rate of cooling is increased, the carbon will have less time to migrate to form carbide at the grain boundaries, but will have increasingly large amounts of pearlite of a finer and finer structure within the grains. Hence, the carbide is more widely dispersed and acts to prevent slip-off defects within those grains, resulting in hardening of the steel. At the very high cooling rates produced by quenching, the carbon has no time to migrate but is locked within the phase center austenite and forms martensite. Martensite is highly strained and stressed supersaturated form of carbon and iron and is exceedingly hard but brittle. Depending on the carbon content, the martensitic phase takes different forms. Below 0.2% carbon, it takes on a ferrite BCC crystal form, but at higher carbon content it takes a body-centered tetragonal structure. There is no thermal activation energy for the transformation from austenite to martensite. Moreover, there is no compositional change, so the atoms generally retain the same neighbors. Martensite has a lower density than does austenite, so that the transformation between them results in a change of volume. In this case, expansion occurs. Internal stresses from this expansion generally take the form of compression on the crystals of martensite and tension on the remaining ferrite, with a fair amount of shear on both constituents. If quenching is done improperly, the internal stresses can cause a part to shatter as it cools. At the very least, there goes internal work hardening and other microscopic imperfections. It is common for quench cracks to form when steel is water quenched, although they may not always be visible. Heat treatment. There are many types of heat treating processes available to steel. The most common are annealing, quenching, and tempering. Heat treatment is effective on compositions above the eutectoid compositions. Hypoeutectoid steel does not harden from heat treatment. Annealing is the process of heating the steel to a sufficiently high temperature to relieve local internal stresses. It does not create a general softening of the product, but only locally relieves strains and stresses locked up within the material. This process goes through three phases: recovery, recrystallization, and grain growth. The temperature required to anneal a particular steel depends on the type of annealing to be achieved and the constituents of the alloy. Quenching and tempering first involves heating the steel to the austenite phase, then quenching it in water or oil. This rapid cooling results in a hard but brittle martensitic structure. The steel is then tempered, which is just a specialized type of annealing, to reduce brittleness. In this application, the annealing process transforms some of the martensite into a cementite, or spheroidite, and hence it reduces the internal stresses and defects. The result is a more ductile and fracture-resistant steel. Steel production. When iron is smelted from its ore, it contains more carbon than is desirable. To become steel, it must be reprocessed to reduce the carbon to the correct amount, at which point other elements can be added. In the past, steel facilities would cast the raw cast iron product into ingots which would be stored until use in further refinement processes that resulted in the finished product. In modern facilities, the initial product is close to the final composition and is continuously cast into long slabs, cut and shaped into bars and extrusions and heat-treated to produce a final product. Today only a small fraction is cast into ingots. Approximately 96% of steel is continuously cast, while only 4% is produced as ingots. The ingots are then heated in a soaking pit and hot-rolled into slabs, billets, or blooms. Slabs are hot-cold rolled into sheet metal or plates. Billets are hot-cold rolled into bars, rods, and wire. Blooms are hot-cold rolled into structural steel, such as I-beams and rails. In modern steel mills, these processes often occur in one assembly line, with ore coming in and finished steel products coming out. Sometimes after a steel's final rolling it is heat-treated for strength, however this is relatively rare. History of steel making. Ancient steel. Steel was known in antiquity, and possibly was produced in bloomeries and crucibles. The earliest known production of steel are pieces of iron were excavated from an archaeological site in Anatolia and are nearly 4,000 years old, dating from 1800 BC. Horace identifies steel weapons like the falcator in the Iberian Peninsula, while Noric steel was used by the Roman military. The reputation of cerric iron of South India amongst the rest of the world grew considerably. South Indian and Mediterranean sources including Alexander the Great recount the presentation and export to the Greeks of 100 talents worth of such steel. Metal production sites in Sri Lanka employed wind furnaces driven by the monsoon winds, capable of producing high-carbon steel. Large-scale wood steel production in Tamilakam using crucibles and carbon sources such as the plant Avram occurred by the 6th century BC, the pioneering precursor to modern steel production and metallurgy. The Chinese of the Warring States period had quench-hardened steel, while Chinese of the Han Dynasty created steel by melting together wrought iron with cast iron, gaining an ultimate product of a carbon intermediate steel by the 1st century AD. The Haya people of East Africa invented a type of furnace they used to make carbon steel at 1802 degrees Celsius nearly 2,000 years ago. East African steel has been suggested by Richard Hooker to date back to 1400 BC. Wootz steel and Damascus steel. Evidence of the earliest production of high-carbon steel in the Indian subcontinent are found in Kodumanal in Tamil Nadu area, Golconda in Andhra Pradesh area and Karnataka, and in Samanalaurawa areas of Sri Lanka. This came to be known as Wootz steel, produced in South India by about 6th century BC and exported globally. The steel technology existed prior to 326 BC in the region as they are mentioned in literature of Sangam Tamil, Arabic and Latin as the finest steel in the world exported to the Romans, Egyptian, Chinese and Arab worlds at the time, what they called cerric iron. A 200 BC Tamil trade guild in Tisamaharama in the southeast of Sri Lanka brought with them some of the oldest iron and steel artifacts and production processes to the island from the classical period. The Chinese and locals in Anuradhapura Sri Lanka had also adopted the production methods of creating wood steel from the Chera dynasty Tamils of South India by the 5th century AD. In Sri Lanka, this early steel-making method employed a unique wind furnace, driven by the monsoon winds, capable of producing high-carbon steel. Since the technology was acquired from the Tamilians from South India, the origin of steel technology in India can be conservatively estimated at 400–500 BC. Wood, also known as Damascus steel, is famous for its durability and ability to hold an edge. It was originally created from a number of different materials, including various trace elements, apparently ultimately from the writings of Zazimos of Panopolis. However, the steel was an old technology in India when King Porus presented a steel sword to the Emperor Alexander in 326 BC. It was essentially a complicated alloy with iron as its main component. Recent studies have suggested that carbon nanotubes were included in its structure, which might explain some of its legendary qualities. Though given the technology of that time, such qualities were produced by chance rather than by design. Natural wind was used where the soil containing iron was heated by the use of wood. The ancient Sinhalese managed to extract a ton of steel for every 2 tons of soil, a remarkable feat at the time. One such furnace was found in Samana-Lorawa, and archaeologists were able to produce steel as the ancients did. Crucible steel, formed by slowly heating and cooling pure iron and carbon in a crucible, was produced in Merv by the 9th to 10th century AD. In the 11th century, there is evidence of the production of steel in Song, China, using 2 techniques: a Bergenesque method that produced inferior inhomogeneous steel, and a precursor to the modern Bessemer process that used partial decarbonization via repeated forging under a cold blast. Modern steel making since the 17th century. The first step in European steel production has been the smelting of iron ore into pig iron in a blast furnace. Originally employing charcoal, modern methods use coke, which has proven more economical. Processes starting from bar iron. In these processes, pig iron was refined in a finery forge to produce bar iron, which was then used in steel making. The production of steel by the cementation process was described in a treatise published in Prague in 1574 and was in use in Nuremberg from 1601. A similar process for case hardening armor and files was described in a book published in Naples in 1589. The process was introduced to England in about 1614 and used to produce such steel by Sir Basil Brooke at Coalbrookdale during the 1610s. The raw material for this process were bars of iron. During the 17th century, it was realized that the best steel came from Öregrunds iron of a region north of Stockholm, Sweden. This was still the usual raw material source in the 19th century, almost as long as the process was used. Crucible steel is steel that has been melted in a crucible rather than having been forged, with the result that it is more homogeneous. Most previous furnaces could not reach high enough temperatures to melt the steel. The early modern crucible steel industry resulted from the invention of Benjamin Huntsman in the 1740s. Blister steel was melted in a crucible or in a furnace, and cast into ingots. Processes starting from pig iron. The modern era in steel making began with the introduction of Henry Bessemer's Bessemer process in 1855, the raw material for which was pig iron. His method let him produce steel in large quantities cheaply. Thus mild steel came to be used for most purposes for which wrought iron was formerly used. The Gilchrist-Thomas process was an improvement to the Bessemer process, made by lining the converter with a basic material to remove phosphorus. Another 19th-century steel-making process was the Siemens-Martin process, which complemented the Bessemer process. It consisted of co-melting bar iron with pig iron. These methods of steel production were rendered obsolete by the Lintz-Donowitz process of basic oxygen steel-making, developed in the 1950s, and other oxygen steel-making methods. Basic oxygen steel-making is superior to previous steel-making methods because the oxygen pumped into the furnace limited impurities, primarily nitrogen, that previously had entered from the air used. Today, electric arc furnaces are a common method of reprocessing scrap metal to create new steel. They can also be used for converting pig iron to steel, but they use a lot of electrical energy, and are thus generally only economical when there is a plentiful supply of cheap electricity. Steel industry. It is common today to talk about the iron and steel industry as if it were a single entity, but historically they were separate products. The steel industry is often considered an indicator of economic progress, because of the critical role played by steel in infrastructural and overall economic development. In 1980, there were more than 500,000 U.S. steel workers. By 2000, the number of steel workers fell to 224,000. The economic boom in China and India has caused a massive increase in the demand for steel in recent years. Between 2000 and 2005, world steel demand increased by 6%. Since 2000, several Indian and Chinese steel firms have risen to prominence, such as Tata Steel, Shanghai Baosteel Group Corporation and Shagang Group. ArcelorMittal is, however, the world's largest steel producer. In 2005, the British Geological Survey stated China was the top steel producer with about one-third of the world's share. Japan, Russia, and the US followed respectively. In 2008, steel began trading as a commodity on the London Metal Exchange. At the end of 2008, the steel industry faced a sharp downturn that led to many cutbacks. The world's steel industry peaked in 2007. That year, ThyssenKrupp spent $12 billion to build the two most modern mills in the world, in Calvert, Alabama and Sepetiba, Rio de Janeiro, Brazil. The worldwide Great Recession starting in 2008, however, sharply lowered demand and new construction, and so prices fell. ThyssenKrupp lost $11 billion on its two new plants, which sold steel below the cost of production. Recycling. Steel is one of the world's most recycled materials, with a recycling rate of over 60% globally. In the United States alone, over 82 million metric tons was recycled in the year 2008, for an overall recycling rate of 83%.